Okay, so welcome to our fourth day, which is on the data economics and machine learning. Bo Waggoner is our lecturer today, and also one of the co-organizers with me of this winter school. When Rita said let's do a winter school, and we agreed to do it on data economics, I was like, I need to bring in like the big guns. And Bo was doing data economics way before it was cool. His PhD's from Harvard, working with Yiling Chen. His postdoc is from Microsoft Research, New York. And I remember, interacting with Bo when I was on sabbatical at Harvard, and the stuff he was doing with Yiling at that time for his PhD thesis was, exactly anticipating this fundamental importance and difference that we're going to have thinking about economic and game theoretic questions when we try to think about data. And so, as I said, doing it far before it was cool. And then people like me come along and are like, oh, this is important now. I better read all of Bo's papers. And so it's fantastic that we have him here talking about the connections between data economics and machine learning.
Okay, unmuted. Well, thank you very much, Jason. It's really my pleasure to be here. I feel very fortunate to get to come to this and interact with you all and speak. Today we'll cover data economics and machine learning. Then we'll probably have some time at the end, and we can move on to add some extra topics. No, it's a huge potential array of things one could talk about, right? Today we're going to see a very specific lens. It's going to be based very much on the perspective that Jason was teaching us about on Tuesday. So it's going to be one specific lens, but it does connect the sort of micro foundations of value of data, of information with value of data. And it will connect to all 4 other lectures this week. So thank you for paying attention closely and learning so far. You should have also learned Friday's material so that you're well prepared for today. It will set up well for marketplaces for data. The narrative that we're going to sort of follow will be talking about what does information look like. We've already seen a lot of this. And in a sort of Bayesian and economics game theory setting, information looks like signals. So we'll talk about what those look like. And then we'll talk about, okay, well, we've already seen this really. Information leads into decision making. And from there, you can get to things of like value of information. We've already seen this, so we'll be kind of recapping it. And then I'll lead that into methods to procure information, which will be based on a tool called prediction markets. And we'll see how that connects foundationally to these notions. Then we're going to kind of do it again. But in a sort of machine learning setting, signals really could be replaced by data, right? Information comes in the form of data. Okay. Decision-making could be replaced by learning or predicting. Okay, it's really not that different. I'll say learning. But right, instead of choosing some decision, maybe we need to output some model, machine learning model that makes predictions or does other tasks. So value of information, how does it change with data? And that'll actually be kind of a relatively brief part at the end, but it will tie together these 2 perspectives. In learning, if we have time, we'll get into a little bit kind of loss functions and design of loss functions, which I think is a nice topic to see. But we'll see how time goes. And then we'll talk about, okay, we talked about procuring information when it's in the form of Bayesian signals, and prediction markets we'll see as a tool for doing that. Can we do an analogous thing with analogous properties when the information is in the form of data rather than Bayesian signals? Okay, so I hope that makes sense, and I hope, if not, that it definitely makes sense by the time we get to the end. So more specific outline. We're going to start by talking about Bayesian updating, beliefs, geometry of beliefs. It'll overlap with some stuff we've seen before. I'll try to go quickly through all of this up to, we've seen value of information before, coming from using that information to make decisions in some decision-making context. And then I'll talk about substitutes and complements of information. So that'll be newer stuff. And that'll lead into this idea of designing prediction markets. And that'll be this narrative as it relates to Bayesian information. We will have less time to do the data side, but it'll build on the Bayesian economics side. So we'll talk about loss functions, time permitting surrogate losses, and how different loss functions relate to each other, so relationships between losses. And then again, value of data and markets for data, where information here is represented as data. Cool. Please stop me and ask questions, add comments. Yes, let's go.
It's cool because also he was asking, who is Mr. Cool?
Who is Mr. Cool? That's the question?
Yeah, because
Okay.
I was also mentioning him. I was wondering who is this guy.
I think whoever is wearing the hat is the coolest. And in this room, I see one win. Okay, two winners.
So we should elect the Mr. Cool of this conference.
Yeah. Also, let me know if my writing is too small in the back or illegible anywhere, although our recourse will be somewhat limited if that's the case. All right, so we'll start with a little bit of setup, some notation that we'll be using throughout. So we'll have random variables, which I'll use a capital letter for random variables. So Y will be an important one, A and B. For a lot of it, those will be the three random variables that we'll be considering. They're drawn jointly according to a distribution pi. Okay, some prior distribution. We'll talk about agents and what they know later, but these are random variables coming from a distribution. Pi formally is an element of the set of distributions on calligraphic Y cross calligraphic A cross calligraphic B. Okay, and I'm going to think of all of these as finite sets. Okay, so the random variable Y takes values in this finite set calligraphic Y, and so forth. Okay. And I'll write, for example, pi of little y, little a, little b for the prior probability, right, that the random variable y equals y, a equals a, and b equals b. Okay. Okay, so far, good. Okay. So okay, we're going to talk about geometry of beliefs. We're going to be in a setting where y is the random variable that's what we would call payoff relevant. Okay, so I'm going to be making a decision in the world, and the thing that impacts my utility is going to be y. A and b are going to be correlated with y, hopefully, and there'll be signals or pieces of information that if I see them, give me information about y. So we're going to be thinking about how your belief about y changes as you receive information. Okay? So a lot of the time we're going to be thinking specifically about beliefs in this set delta of calligraphic y specifically, the set of probability distributions on y. And just as a reminder, as you know, this is the set of vectors q in r to the, let's say, size of y, such that, okay, q of y is non-negative for all y, and the sum is 1. Okay. Probability distributions on y, and I'll have a specific notation. Let's use some bullet. I'm going to try to always write p when I mean the prior on y. On the random variable y. So it's the marginal of pi on this random variable y. Okay. Everyone okay with that? And p sub, for example, p sub a is going to be a posterior. It's going to be the posterior given on y, given, sorry, this writing's getting small, I'll try to fix that, given the information that capital A equals this little a. Okay, and let me just formalize that. So PA of y, the posterior probability of y, can also be written in my notation as just pi of y given A, shorthand for the probability that capital Y equals this, given that capital A equals this. And by the way, let's recall our definition of conditional probability. It's going to be used a lot. So that's the probability that both happen, y comma A, renormalized by the probability that A happens. Right. Okay. In a lot of stuff I do in this field, conditional probability is happening all the time. If you remember this definition, and if you're dealing with conditional probabilities and you replace them with the definition, often that's what you need to do to be able to work through problems. You also don't need to remember Bayes' rule if you just remember the definition of conditional probability. You just apply it a couple times and it'll give you Bayes' rule. So just to recap, we know this, but good. So let's talk about how beliefs evolve. And again, these are going to be introductory things that many of you know, or you know but you haven't phrased in notation yet, but are not surprising. But let's think about, okay, the weather tomorrow. I did not have a more creative example of things we want to predict. So calligraphic Y is going to be either sun or cloud or rain. We're going to include rain as a possible outcome. Just, who knows? Once in a century, it might happen here.
Every month.
Yes?
Every month, every 10 years.
Okay. Yeah. So it's a possible outcome. And I'm new to Morocco, so my prior belief, for example, let's say P is uniform, 1/3, 1/3, 1/3. And we can represent this belief as a point in the probability simplex, which you're all familiar with. It's this set. One thing to note, because this happens a lot, I get confused by it, people get confused by it. This is a point in R3. Let's draw the probability simplex in R3. Okay, it's going to look like this triangle. Okay, this is the set of points that are non-negative and sum to 1. Okay. Now, of course, it's more convenient to draw this triangle as follows, like this, where I'm going to put the probability that, the distribution that puts probability 1 on sun, I'll put it at the top. The distribution that puts probability 1 on cloud, I'll put it here. Okay. And I think Jason gave us some diagrams like this already. Good. And my prior P is right here in the middle. It's the uniform distribution. Okay. Good. Okay, so if for my belief to evolve, I need to get some information. Let's have a signal A. And I'm going to have calligraphic A. I go outside and I observe the wind, and it's either windy or it's calm. Okay. And I observe one of those two things, and I'll update to a Bayesian posterior belief given what I observe. And let's do an example. So let's suppose, for example, that P sub wind, my posterior distribution on the weather tomorrow, given that I've seen it's windy, is 1, 0, 0, indicating a probability 1 of sunny tomorrow for whatever reason. I'm not a great weather forecaster. So P wind is here. Okay, and again, let's suppose in an example that P sub calm, I see that it's calm out, and I decide it must be cloudy tomorrow, 0, 1, 0. Okay. Okay, so there's a problem with my example. What's the problem? What's the problem with these three beliefs?
The average of P wind and P calm should be the prior.
Yeah, so why should that be?
You can always, the conditional probability the weather forecast of Y given A, right? You can partition it.
Yeah, right. So there are two possibilities. Either A is wind or A is calm. If A is wind, I already said it's not gonna rain. If A is calm, I said it's not gonna rain. How could I believe that there's a 1/3 chance of rain if I believe that no matter what happens with A, it will not rain? Okay, this is not possible. Okay, this is not a possible Bayesian information structure because of a fact that is exactly what you said. So it always holds that the expectation of my posterior is equal to my prior on Y, for example. Notation, here capital A is a random variable. This is my expectation of my posterior belief, which is now a random variable. So let's adjust this. Let's suppose in a correct example, my prior P is right here, 1/2 sun, 1/2 cloud. With half probability, I expect my posterior to be this point. With half probability, I expect it to be this point. The average is my prior. Okay, so another way to say this is my current belief is always an unbiased estimator for my future belief. Another way to say it is a Bayesian's beliefs form a martingale, which is something you may have run into. I'll do a one-line proof just to kind of familiarize you with my notation. Okay, so what is the expectation of PA, capital A? That's the sum over all realizations of my signal that could happen, little a, of the probability of that realization. Excuse me, let's fix a particular outcome y, and we'll prove that the y-th coordinate of this vector is equal to the y-th coordinate of this vector. Okay, so my posterior, the expectation of my posterior belief of the coordinate y is the sum over a, probability of y given a. Where again, this is just a way to rewrite P sub a. Okay. Now by rules of probability, the probability of a times the probability of y given a is the joint probability of y and a both occurring. Okay, we're practicing how could I get that? I could use the definition of conditional probability. I could expand this as the joint probability of y and a over probability of a, and it would cancel. But okay, so this is equal to the sum over a, probability of y and a. Again, some laws of the law of total probability. This is the sum over all of the ways that y could happen. Right? So for concreteness, let's suppose y is sunny. It's the sum over wind of the probability that it's sunny and windy, plus cloud times the probability of sunny and cloud. All the ways that sunny could happen. When I sum over all a, I'm just going to get the probability of, in this case, sunny. And that's the same, the prior probability of y in my notation. Okay, I hope this was just helpful in kind of anchoring how I'm using the notation here. But are there any questions? Definitely let me know if so. Okay. By the way, there's a converse of sorts, which is the following. If I ask a question, suppose I have a set of points that I want to think of as possible posterior beliefs that I might update to. So imagine a signal with 5 possible realizations, and I have 5 points here, which says for each of those what my posterior belief about y would be, if I saw that. And I have some point in the simplex, and I want to ask, is it possible, does there exist a distribution pi, a joint distribution pi, where this is the prior, and these are the posteriors? So it definitely needs to be the case that this supposed prior is in the convex hull of these posterior distributions. If not, you have a contradiction similar to what we had in my original example. Is that sufficient if it's in the convex hull? It actually is sufficient. Yeah. Yes. So as long as this point is in the convex hull, by definition, you can write this point as a convex combination of these possible posterior beliefs. And that convex combination is basically giving you a sort of conditional probabilities. They're basically these. This is a convex combination of, this is the convex combination of these posteriors. So I'll write that quickly as fact 2 without spelling it out. Converse. So for any collection PA and any P in the convex hull, there exists a prior distribution pi consistent with those. Okay, cool. Okay, so that's just a quick kind of getting used to how beliefs evolve. We did a case of one signal. The case of adding a second signal is just going to repeat this idea, right? So I learn one piece of information. Let's say, let's go to my new example here with the green points. I started with a prior P. I learn one piece of information, let's say capital A, the random variable, and I update to a posterior based on it, one of these points depending on the realization, let's say this one. And now if I'm going to learn capital B, again, PA is going to be an unbiased estimator of where my belief will end up after I learn the next piece of information. Okay, so it'll be in the convex hull of the beliefs I might update to once I learn B, and the expectation of my future belief is my current belief, and so on and so forth. You can kind of see that the space of beliefs seems to kind of expand outward because of this convex hull idea. But yeah. Good, okay, so now let's kind of recap value of information, which we've already learned. Okay. So recall, restate, that we have a decision problem U of Ry. U is this utility function. R is an action that I'm using R here for our action sets. So we're going to choose one of our available actions. Nature is going to realize this random variable y, and our utility will be U of Ry. We've seen that. And given a belief, some notation. So if I have a belief Q in the simplex on Y, I'll write U of R given Q as the expected utility for action R, given that Y is drawn, well, okay, I should write it this way. So given that Y is distributed according to Q, my expected utility for taking this action. Okay, I'll redraw that geometric picture in just a moment. But given U, we can also define G, a convex function G. It turns out to be convex. G of Q, which is the maximum utility that I could expect to get if I have belief Q. Okay. G of Q, and we'll draw the picture in a moment. Another way to write this is the capital U of RQ given Q, where RQ is the best action given that you have belief Q. I think we saw that notation. Right? That's the argmax of the maximization. Okay, let's draw the picture. So on Tuesday, we saw a decision problem that looked something like this. something like this. Each of these lines was an action. Okay, this was, I don't remember what, but these are two outcomes of the random variable y. I'll just call them 0 and 1. In between, we have beliefs q. I'm doing the same thing I did over there. This is the probability simplex on two outcomes. Really, I should draw it like this line, right? The simplex, this is distributions that put probability 1 on a certain outcome. These are distributions that put probability 1 on another outcome. This line is really this line, and I'm going to draw a function above that line. Something I like to keep in mind because I get confused about it if I forget it for too long. Each of these lines was an action, okay? And this was, for example, the payoff of this action if y equals 1, and this was the payoff of this action if y equals 0. And this action also had payoffs. Our convex function g turned out to be convex, is this v-shaped function in this case. It's the pointwise maximum as I sweep over q of the utility I could possibly get in expectation if I have belief q. Right? And we saw all that. Great. But questions about this? Yes?
In the previous one, if P, the prior, has a coordinate 0, where you have posterior belief, that's not going to be consistent, right?
Right. So if your prior belief is that some value of y has 0 probability, all of your posteriors will also have that. Yeah. Good. Okay. So something we saw was a revelation principle. I think I'll skip writing it down, which said for any decision problem, we can also define a proper scoring rule where the utilities match. The utility of predicting q to the proper scoring rule is the same as the utility of deciding in the decision problem where you take the optimal action for belief q. So we like that because we can think of, okay, scoring rules are a very special case of decision problems, but we only have to think about scoring rules. As long as agents act optimally, we don't have to worry about all possible decision problems. We can worry about all possible scoring rules. That's nice because we have this important characterization theorem, which I will restate. This is slightly different than we saw in lecture, because this is only going to apply to scoring rules for probability distributions. And as you recall, in lecture, we saw a characterization for scoring rules where you're predicting the mean of a random variable. And in this case, well, that's actually more general, but we're not going to talk about why. But a scoring rule, S of Ry, is proper. Oh, what was the definition of proper? Let's recall. It's been one day since we talked about proper scoring rules. A scoring rule is proper if you maximize expected score by reporting, and in fact, let me put Q here because you're always reporting a distribution. You maximize expected score by reporting the distribution Q that you actually believe. And again, that's your subjective expected score. Given that you currently believe Q, you maximize expected utility by reporting Q. And it's proper if and only if there exists a convex function G such that the score can be written as follows. I'll write it this way. Okay, so the score can be written as this formula that takes G and sort of generates the score. What are the components of this formula? Okay, G of Q says G of Q. The angle brackets here are just an inner product. It's just a dot product here of two vectors. dg of Q is a subgradient, but really for today, anytime you see that, I will keep using it because it emphasizes that convex functions have these things called subgradients. But you can always think of this, especially today, as just the gradient of the convex function G at Q. And know that sometimes convex functions aren't differentiable. For example, this point function at this point. But they still have a subgradient, which is roughly, actually a set of them, which is roughly any slope that allows a line to still stay below the function. Think of the gradient. Delta y
if you have a subgradient, you have many subgradients. Which one you take?
Yes. So there exists a choice. Actually, for any choice of subgradient, if you have multiple options, you will get a proper scoring rule. The reason is that all of the subtangent lines lie below the convex function.
So you do some selection.
Yeah, but
But you want the selection to be continuous on Q.
Not necessarily. Yeah, like here the selection.
Scoring can be
One.
discontinuous. You can have a,
Yeah, it can be discontinuous in your report. And this is an example where, yeah, as you change your belief, your report from here to here, your payoffs are very discontinuous. Yeah. And then this delta y notation, this is just a vector that is all zeros except for a 1 in some coordinate. I like to use this quite a bit. A 1 in the yth coordinate. Okay. Delta y minus q. Okay. Geometrically, we saw some of this, but I like to restate it, and I'm going to give an example with a strictly convex G. So geometrically, your score for predicting Q, when we say outcome Y, is G of Q, start at this point, plus the slope of G, dot product with the vector that goes to the outcome that actually happened. That's delta Y minus Q. Okay, so I take the slope and I dot product with the outcome that actually happened. This is my score, S of Qy. So given the convex function G, I create this proper scoring rule. We saw at least a lot of this. And on the other hand, of course, we take this to the other end. Okay. And now you can try to picture how that looks in a probability simplex with 3 outcomes. I have a convex function sitting out here in space. The gradient gives me a tangent hyperplane below the convex function at the point. And then I evaluate that tangent hyperplane at each outcome, and that'll tell me the score of this report where it's tangent if each of these outcomes happen. Awesome. Okay. Questions? Sorry if I'm blocking that. Okay.
To prove one
yes.
direction is clear. The other direction is separation argument, I guess?
Not even. Yeah. So did they do this in the recitation? Is Matthew? Something very similar is on there. So one direction is you say, okay, if it has this form, it's proper. The other direction is to say, suppose it's proper. Well, actually, this is a fact I want to mention next. Or at some point. This expected utility, that's this line as a function of Q. It's linear. It's always linear in your belief. So every report, any decision problem, in particular any scoring rule, each report defines a linear function. What does it mean to be proper? It means that at Q, your particular linear function is the maximum over all the others. And we can trace G out as the pointwise maximum of these linear functions. And that's pretty much it. That's pretty much the proof. Yeah, it's
Convex is characterized by the hyperplane.
yeah, so
This gives you a function.
yeah, convexity is characterized by being a pointwise maximum of hyperplanes, except in super annoying weird cases where you have a discontinuous convex function, and yeah. Good. Your decision problem and fix your prior. Then define V with respect to U. Well, there's also a pi in this value function, but I'll emphasize the U here by writing it. The value of, okay, no information I'm going to represent with this bottom symbol. No info. So the value of not having any information at all. If you don't have any information at all, what's your expected utility in the decision problem? Actually, okay, this may rely on a fact that I want to write? Yes, okay. Let me write that fact first. Then this will be very easy. I wanted to consider a fact that will help us work with this definition, which is what is the difference in expected score if I believe Q for reporting Q truthfully versus reporting something I don't believe Q prime. My claim is this is, well, it's going to turn out to be the Bregman divergence of this convex function G, and we'll see why, and we'll see what the definition is. So my claim is this is G of Q minus, okay, something that looks very similar to what we've seen. Nope. Okay. Why is this term equal to this? Good. Good, okay. So the first thing to note is if this is your score for outcome Y, what's your expected score for belief Q? Let's just do for belief Q. Well, let's take the expectation over all of this with respect to the random variable Y. This is a constant, doesn't depend on Y. This doesn't depend on Y. This doesn't depend on Y. This does. What's the expectation of the indicator vector when it's drawn from a distribution? It is the distribution. Okay, so this becomes Q. But okay, so S of QQ, your expected utility for reporting Q when you believe Q, you get a 0 here, and it's just G of Q. So I'll refer to G as your expected utility function that's associated with the decision problem that you're dealing with. It traces out for any Q your expected utility when you have belief Q, assuming you act optimally. So that's why this term is equal to this term. And now this term equal to this, well, we just plugged it in. It's really just taking linearity with respect to Q, and we get a Q here instead of a delta Y. But now this is a well-known expression, which is the definition of a Bregman divergence, which I'll use dg to denote, between Q and Q prime. And this has a picture, which is, okay, this is actually going to be my Q prime now. This is going to be my Q. Here's G of Q. And this point is everything else. It's G of Q prime plus the gradient at Q prime dot Q minus Q prime. So this height is the Bregman divergence. Okay. It's kind of a side fact, but it will come up later. Good, okay. Okay, so the value of acting with no information. Intuitively, what's the value of acting in the decision problem if you have no information? What's your expected utility? If I have no information, I'm using this notation. So in terms of G, it's G of P, G of the prior. So I'll just define this to be G of the prior. Similarly, my value for acting, given that I'm going to have access to the signal A before I make my action, it's going to be, and I'll write it as a sort of a priori, expectation over A, G of PA. Okay? So I have not yet seen A. In expectation over what I see from A, I will update to some posterior, and then I will act on that posterior, and I'll get G of that posterior in expectation, because I always act optimally given a belief. Okay, good. So next fact. No, okay. Comment. The difference between these is the marginal value of A to my problem, is the term that I'll use. It's the marginal value of the signal A. And so fact, I'll go ahead and write it down here, but I'll say it out loud in case anyone's having trouble seeing it. Fact number 3. More information always increases your expected value in a decision problem. Jason already told you this fact, or probably proved it. And-
zero-sum games.
And it's also true in zero-sum games and not true in other games. People say life is a game, but my life is a decision problem. So for me, more information always helps. Okay. So yeah.
Let's talk about this later.
Yeah.
because there are many possible extensions of this. So many game theorists try to extend Blackwell order to context, or to value information.
In
using
games.
zero-sum games.
Okay.
As functions. As
Good.
functions, and you can repeat all the Blackwell order, and it's much more interesting because you have some. So Mertens, for example, is one of them. Olivier Gosselin, perhaps you may know him. Also
I don't think so.
that.
Yeah.
So there are many things that has not been done yet
Yeah.
that can be interesting to do.
Awesome. Yeah. And this concept that we like in computer science of persuasion could kind of fall into this category. You're introducing information into a game to change what happens. And it's not clear that it always helps people to have the information when it's in a game. Okay, so the left side here is my value or utility of having A. The right side here is my value of acting without A. I'm asserting that you have more expected utility when you have access to A than when you don't. Okay, and this is actually Jensen's inequality. What is Jensen's inequality? It says for any random variable, well, let me just, so why is this? The right-hand side is G of the expectation of your posterior. This is by fact 1. So G of P is G of my expected posterior. Everyone agree with that? Jensen's inequality is a fact in probability and convex analysis that says for any convex function, the expected value of that convex function is at least the convex function evaluated at the expectation. Okay, in the picture, and again, Jason has drawn this picture. Let's suppose now, I'll take the same picture, but here's my prior, here's one of my posteriors, and here's another. I won't need this. Okay. My expected value for acting without information is G of P. My expected value for acting, given that I see A, is going to either be here or here, depending on which I see. In expectation, it'll be here, and this gap is indeed the difference between the left-hand side and the right-hand side. For a convex function, it's always non-negative. You can get 0 if you have a flat linear function. Okay, that's Jensen's inequality, and that's the same as saying more information helps. So, okay. So I would say at this point we're caught up and hopefully reinforced concepts that we've seen. We're familiar with my notation.
A comment that can be useful for everybody.
Please.
So if you have an advisory,
Yeah.
okay, you will minimize in some action B. So your
Yeah.
plane is minimizing. So when you minimize a linear function, it's a minimization of it's a concave function.
Mm-hmm.
Minimum, yes, it's a concave function. Now, if when you do all these operations, you can prove that you still have this property of convexity that still hold when you're doing your optimization, and you still have this all these properties even if you have an adversary. But it will not be the case otherwise. So that's why all these tools extend to work with adversary. But I guess in computer science, having adversary is also good. If you decide in face of adversary, you still have all these properties holding.
Awesome. Yeah. Great. Okay. So now I want to talk a little bit about garblings. I feel this word has come up a lot this week for me in discussions. I don't know if that says something about the way I speak or convey information, but there's a rule for this section that's specifically for our front row. The rule is you're not allowed to say the word Blackwell until I say the word Blackwell.
Okay.
Actually, you can't say it until I've said it 4 times, and so far I've only said it twice. Okay. So we're going to define A is independent of Y, conditioned on B.
I'm learning a lot from your course. I don't know all this stuff.
Okay, okay.
I'm just anticipating or linking some stuff I know, but of course I'm learning. That's why I'm here.
Yeah, good. No, good. Yeah. Yeah, no, I more meant, from Tuesday, we've seen most of this in a slightly different way. But yes, yeah, that's great. So A is independent of Y conditioned on B. If, here's one way to define it, if the probability of A given B and Y, well, intuitively, what's this saying? It's saying that it doesn't matter what Y is if you know B in terms of the distribution of A. So it's just the probability of A given B. B for all A, B, Y, for all realizations. Okay. So that's conditionally independent. It's a lot of words to write. I'm a slow writer, so I'm going to write this as A precedes B. It's, I'm stealing this notation from the theorem that must not be named. And this should really be like a Y here, but I'm just going to write this as shorthand for this statement. Because in my setting, Y is always this payoff relevant random variable. And so everything is sort of relative to Y in my setting. Good. Okay. Examples. Let's say B is the temperature outside. I'm very worried about the weather and all of my examples. It's on my mind all the time. A is going to be the temperature rounded to the nearest degree. I'll just say temperature rounded to the nearest degree. Where sadly, the weather app on my phone doesn't give me those decimal digits that I really want. It just rounds the temperature to the nearest degree. A is going to be independent of anything like rain tomorrow, conditioned on B. Right? If you tell me anything at all about whether it rained or not, anything you tell me about Y is not changing my belief about A given B. Well, that's because A is, in this case, a deterministic function of B. Well, that makes it pretty clear in this example. Sometimes things like this in econ are called pooling, because you're taking many, many possible observations that you saw and grouping them together, pooling them into fewer reports. Okay, another example. B is going to be the exact wind speed and direction. And A is going to be where my hat landed when it blew off my head. Okay? I'm going to suppose there's some randomness in this process now. Okay? It's not a deterministic function of the wind speed and direction, but it certainly doesn't depend on whether it rains tomorrow or not. There's no correlation there outside of the correlation introduced by the wind speed and direction. Okay, so more formally or more generally, you could have any randomized function. A is a randomized function of B. Okay, and we often call this a garbling, and I'm going to try to clarify or say a bit more about this word in a minute. But yeah, so when intuitively, if someone says garbling, this is one of the things they can mean, the main thing they can mean, which is you have this, and then you have some randomized function of it, A, and A doesn't depend on anything else in the world except for B and some randomness. We've lost some information, and this was the idea yesterday with F-mutual information, where these garblings lose information. So generally, you can't gain information about Y from a garbling. Okay, of course. What else did I want to say? Oh, sometimes garblings are called experiments, and we're going to talk about this in a minute, theorem that must not be named. But it's often called an experiment, and this is kind of an intuition of Y, right? I toss the hat and see what happens, and I've learned something about B. Or I've learned something about Y, not as much as this, but yeah. Okay, good, we're getting there. So you can make different observations, but one I want to point out is that A is independent of y condition on B, if and only if the posterior, let me make sure I get this right. Yeah. My posterior belief about y, if I see both A and B, is my posterior belief about y if I only see B. Question? Comment?
There's some geometric interpretation of this that relates to the triangle. Like, for example, at first I only have a point,
Yeah.
but I lose information, so the new information is going to be a whole set.
Yeah, good. This is also related to the theorem that will eventually be named. Let's say these are all the PB, all the posteriors conditioned on B. Well, if I garble B, that's like saying one thing you could do is I observe B, and then as a function of what I observe, I emit a signal, or I emit A as a function of what I observe. And yeah, for example, your belief condition on seeing A can't go outside this convex hull. Actually, what this claim is saying is that if A is conditionally independent on B, yeah, A tells you nothing more. Your belief stays right here. And then, but on the contrary, for example, if I first learn A, it could tell me something, and then B could tell me a little bit more, right? Because it's hiding things. Yeah. Good. Okay. So that's one observation you can make about this, but you can kind of make, let me say something in 1 minute when I write down fact number, well, all right, let's call it a claim. Let's do it here. Okay, so the name of this claim is not exactly Blackwell. That's 3 times. And the content of the claim is that A is independent of Y conditioned on B, if and only if, for all decision problems, the value of A is less than the value of B. I mean, this is the theorem of somebody, but I'll explain the difference. What's it saying? Well, okay, in any decision problem, any convex function, right? From now on, when you hear any decision problem, think over the space of convex functions. For any convex function you draw, it's the case that the value of having A is less than or equal to the value of having B. Well, one direction from what I've written is quite immediate. Suppose that this is true. Then I've claimed, or I've observed, that the posterior, when I get A and B, is the same as the posterior when I get just B. Well, one way to write that is that the value of acting in any particular decision problem of A, well, okay, fact number 3, that's less than the value of acting with both A and B. More information always helps. But by the observation, the value of acting with both A and B is the same as just acting with B. Okay. So this direction's fine. I hope you agree. Geometrically, no, let's skip it. Yeah, but you could draw it with the convex functions and the beliefs updating. The other direction is like tricky, okay? Because, well, I think the way I would say it is, if this is not true, find a utility function, find a decision problem where this inequality does not hold. And that's how you could prove these things, and you need like a separating hyperplane type thing that finds the decision problem that really rewards you for knowing A, but rewards you less for knowing B. An easy case of that would be, okay, if this doesn't hold, one way it could not hold is I have all these posteriors PB, but there's some realization of A that gives me a belief outside the convex hull. This is an example where, so here's PA, and all of these are different PBs. This is an example where A could not be independent of Y condition on B, because this belief is outside the convex hull. And I'll find a decision problem exactly, where I take a separating hyperplane, and basically anything you know, I'm going to create a convex function, right? So I'll just make it flat above this part of the simplex, and I'll make it very steep above this part of the simplex. And so your expected utility, the value of having A will be positive, because sometimes you learn this and you get a positive G, convex function. But your value of B is all in the flat part, and you get nothing from learning B. Now, there are cases where all of the PAs are in the interior, but it's still not possible because there's too much weight, on these or something, so the proof is trickier than that. Okay. Now, yeah, question. Yeah.
Is there a more intuitive counterexample by constructing a convex function for which where we randomize on a part, it basically doesn't satisfy the Jensen inequality sense.
Yeah, I think it's the same problem as what you said, and it may be easier to think of that way. Yeah, yeah. Okay.
So the game analog would be in this side. For every zero-sum game, you get better by knowing. In B, you have better outcome if you have maximizer than A, and then the other side you have an if and only if.
Mm-hmm.
Here it's more complicated.
Yeah, right.
To give the character.
Yeah. Okay, so I'm going to make an aside on Blackwell orderings. So this is my understanding of how an economist frames the Blackwell ordering question, which is intuitively the same as what I've already said, but formally there's slight differences, and I'd rather explain them than skip it and move on, because I've found this difference between the formal setup of Blackwell and what I did. I found that confusing, so let's do it.
It's also called Schoke order.
Yeah, what is the order?
Schoke.
Shaki? Shaki order? Yeah. Okay. Yeah, good. So, okay. Here's Blackwell's setup. It's almost the same as mine, but I'm going to say everything that we need for Blackwell's setup. So y is a random variable. I'm going to frame it in my terms, but let y be a random variable. And let f and g be randomized functions. F is going to go from space of outcomes of y to the space of A, calligraphic A. G is going to go from the outcomes of y to calligraphic B. And they're randomized functions. So they're, well, let's just call them, randomized functions for now. Often these are represented as matrices. What's called like a confusion matrix or a stochastic matrix that's applied as a linear operator to the distribution of y to get you a distribution over points in A and points in B. Okay, so we'll say that f is a garbling of G if there exists a randomized H such that f is the same as apply G, then apply H. Okay. So the difference between this and my little notation here is that these, in my setup, these are random variables that come with a distribution, and they come with a prior distribution. Here, these are mappings. These are sort of conditional mappings. That's this difference. Okay. And now we also say f is less informative than G. If for all priors where A is f of y and B is g of y, and for all utility functions, or all decision problems, we have that the value of A is less than or equal to the value of B. Yeah.
These pi's are distributions over y?
Pi is going to be a joint, thank you, it's a joint distribution over y, A, and B. Consistent, well, yes, consistent with the fact that this holds. And let me dig into that because it's the whole difference. If I just tell you a distribution over y and I give you these, I haven't told you how a and b are coupled. There are two random variables with these marginal distributions. And indeed, okay, the point of connection is this idea that, okay, kind of clearly, f is a garbling of g if and only if there's a way to couple these random variables so that a is independent conditioned on y, conditioned on b of y. Why is that? Well, one thing you can do to have these marginal distributions is have b is g of y, and then a is h of b. Right? First I draw b, and then conditioned on b, I randomize it and I garble it into a. However, in Blackwell's theorem, you can also consider a and b that have the same marginals, but that's not actually how they're coupled. What is Blackwell's theorem? Well, it looks the same as what I've already written. These are equivalent. This is an if and only if. Okay. So it looks very similar to what I said before. It's just that the setup is a little bit different, and I hope this explanation is useful if you run across it in the future. But that's all I wanted to say about it.
General than what
It's like a bit more general
because you're
because
not doing this exact way of producing the correlation.
yeah. So I've assumed that these variables are already coupled in a way that first b is generated and then a is conditionally independent on it. And Blackwell just says, okay, they're two signals, but their conditional distributions have this relationship that it's possible to write one as a garbling of the other. But you should be able to prove Blackwell's theorem from this, because this doesn't really depend on the coupling. Like if this inequality is true, it's true for any way you couple them. It only depends on the marginals. So you just say this is true if and only if it's true for the case where they're coupled as a conditionally independent chain. Well, that's only possible if it is indeed a garbling. Okay. Yes?
So it's still a notion with respect to y.
Right, so they won't necessarily set it up that way in a textbook, but there will be some set of states in the world, and this is for any prior on those set of states of the world, and y will be standing in for that in my, like those are the payoff relevant states.
According to this definition, f might be less informative than g sometimes, but other times g might be more informative, less informative, depending on the underlying.
Yes, right. So these are just stochastic matrices. These are just randomized mappings. And you could have different priors on y that do different things to these, yeah. And then you could couple them in different ways as well if a and b are two random variables. If you haven't seen Blackwell, I understand this might have been more confusing than helpful, and if so, I apologize. But okay, this is what I think is good to know about it. One comment, kind of famously, this is a partial order, right? F is sort of less than G if F is less informative than G. Kind of famously, this partial order doesn't form a lattice, which if you don't know what it is, it's fine. But one thing that's nice is this actually will form a lattice once you kind of enforce. So like once the distribution is fixed, if I look at any sort of collection of random variables with this fixed distribution, then I do get a lattice, and that's kind of nice, and I'm actually going to use that quite soon. Substitutes. So this is where some econ of information, is starting to come in. Well, no, it's been coming in the whole time, but connecting to sort of really economic notions that people in macroeconomics, people all over think about substitutes and complements. So we get to think about that too. When are let's say goods? When are items substitutes? I'm not looking for math, but what does that word mean?
Coca-Cola and Pepsi.
Example: Coca-Cola and Pepsi. Okay.
I would
Pepsi would value both less than the sum of them. Yeah, absolutely. And this formalization is a very common intuition, which is that your value, and I'm going to use A for Coca-Cola and B for Pepsi, just for fun, that your value for having both A and B, one formalization of substitutes is this is less than your value for having A plus your value for having B, for example. Right? So, okay, we're hopefully familiar, intuitively with substitutes, but there are different formalizations of it. I'm going to use one that's slightly different, but it conveys a similar intuition, which is marginal value. I think I'm going to keep writing in blue. It's nice. So this difference here is the marginal value of A to me. If I only have B, I'll get this. But if I have A and B, I'll get this. So it's the marginal, in this case, it's the marginal value of a Coke over already having a Pepsi. The Pepsi is here in my hand. Would I like a Coke? Well, not that much, thanks. Even if I prefer Coke, the amount that I want it is lessened compared to the marginal value of having a Coke if I start with nothing. And so this is the notion of substitutes that I'm going to rely on. And this is capturing what's called submodularity, which I'll define briefly. But a note is you can rearrange this by moving, this over here. It's not that different from subadditivity, which was the first notion we wrote down. The main difference, or the only difference, is that we have this extra term on here. Intuitively, it makes this slightly harder to satisfy than subadditivity. So there's some sort of valuations which are subadditive and not submodular. But it's not that different of a notion. OK. So in this setting that we're going to discuss. Yes?
Is the value the utility in a decision problem? Or?
OK, so far, this is intuition about some function of some things A and B that I haven't defined anything. In this, I mean, A and B had definitions, but this was all intuition. Thank you, yeah. And now I'll try to define something. So in this setting, I'm just going to expand my setting by having possibly more signals. Okay, so that there's a large collection of signals, and they're all jointly distributed according to pi. And for subsets, I'll often write subsets of signals. I'll often use a capital R and a capital, well, a few times I'll use a capital R and a capital T, because I'm low on letters. So R could be a pair of signals, or it could be a set of 7 signals. T could be a set of 10 signals, or the empty set, okay, in this section. The definition of a submodular set function I'll just say F, is that for any subsets R and T, where R is less than T, and for any signal A, I'll write A here, but I mean any signal, adding A to, let's say, to T, the marginal value of A, given that I already have T, is less than the marginal value of A, given that I have R. On this side, I have many things. Do I want A? Do I want to also get A? On this side, I have few things, fewer things. Do I also want to have A? Well, if I don't have very much, I should want to have A more. How could this fail? Well, it could fail if you had something that's intuitively complements. Here I don't have, for example, bread and cheese. Here I don't have anything. Do I want some cheese? Well, I don't really like cheese that much. But now you give me bread. Bread with cheese is really good. Now I want the cheese. that's complements. Okay. If it doesn't hold, that's substitutes. You might, for this definition, you might need A to be something that's not in the set T. It's a technicality. By the way, supermodular would be a definition of complements, and you just reverse the inequality always. In supermodular, the more you have, the more valuable something new becomes. It's sort of less intuitive and less often used, but that'd be complements. Yeah. Yeah. Okay, so we're going to just apply this to value of information. So, yeah. Okay, so definition. These signals, which well, we can just say pi, or I'll say the signals in pi are substitutes with respect to a particular decision problem. So I'm going to fix a decision problem, a utility function, if this VU function is submodular. VU function is probably on the other side of this board. It's the expected utility for acting given access to the stuff in the parentheses.
Something else to understand. Signals in pi. So the signals are the A and B?
Yes, yes, the signals, this is...
So this is given. You have Y, A, B, C, D.
Yes, so this setting is fixed, pi is fixed. These are the signals. Everything but Y is the signal.
The distribution is fixed?
The distribution pi is fixed.
Okay.
Everything
Given
is
pi,
fixed. Yeah.
So signals are substitute with respect to the decision problem U if V of U is submodular. Okay.
Yeah. So let me see if I have an example to think through. Okay, I have a geometric picture for this. This was just intuition. Let's erase. Right, so what does it mean? It means what we were saying. So the more signals I have access to, the more information I'm going to get before I make my decision, the less I want A, the less it increases my value. The more information I have access to out of this collection, the less I want any particular signal. Okay, and we can draw that because VU has a drawing, has a picture associated with it. Okay. Guys, all I do all day is draw a smiley face, make a few lines on. This is where it's at. This is what it does. So let's consider the first signal. I get my first signal, let's say B, and I either update to this PB or to this PB prime, depending on what the realization is. And we saw that the value of the first signal was kind of captured by this. Okay, what's the value of the second signal? Well, let's say I already had B, and then I could either update to like PBA or PBA prime, depending on what happens. And so the marginal value of the second signal here is going to be this. Okay, and the same thing can happen over here. The net marginal value of A, so VU of AB minus VU of B, the net marginal value of A, is the average of these two averaged over the prior. So the average of this little improvement and this little improvement averaged over the prior probability that you're in either case. So that'll be this. And now a diminishing, well, no, I have to be careful. It's the submodular inequality does not compare this to these. Because this is the value of B. This is the marginal value of B. And those was the marginal value of A over B. The substitutes inequality compares the marginal value of A over B to the marginal value of A. To compute that, I need to draw where is my posterior if I only observe A. And then I need to draw that, and I need to see how much value A is bringing me over nothing. I'll say a little bit more before I let you relax. Okay, definition. Signals are complements with respect to U if VU is supermodular. And let's do some real basic examples before we break, and it'll help fix the definitions, I hope. Okay, so if A equals B, meaning with probability 1, the outcome of A is equal to the outcome of B, which of these two notions should they satisfy? I have one answer. Well, one person's still awake. Thank you. You guys are doing great. I really appreciate it. They're substitutes because if I have any one of them, what's the value of the other one going to be? 0. The marginal value will be 0 of if I have either one. So the first one will at least bring me some value, but getting it second will bring me no additional value. Okay. The canonical complements example is the following. A and B are uniform random bits. And they're independent of each other. And we're predicting Y, which is the XOR of A and B. Okay, so it's got computer science-y kind of fast. So Y is 1 if A and B are different, let's say. Is that how it normally goes? And no. Y is 1 if they're the same, I believe, and Y is 0 if... Okay, it's what I said first. It's 1 if they're different, and it's 0 if they're the same. To me, yeah, to me it doesn't matter, but... Right. The value of information in my decisions... Okay. So what's happening here geometrically? If I tell you A, all right, well, what's more prior on Y? It's still uniform, right? If there's a half-half chance, there's a half-half chance that Y is 1 or 0, so my prior on Y is 50-50. Yeah, so what's my posterior if I observe just A going to look like? It's still going to be 50-50. So some of us have seen this before probably, and some haven't. It's still 50-50, right? If A is 1, there's a half chance of either. If A is 0, there's a half chance of either. So P is equal to PA and PB for both, yeah, PA prime and for all the outcomes. The value of the first signal is always 0 in this example. Okay? The value of the second signal is going to be something. You're going to move to one of the two extremes. Your posterior, once you learn both signals, you know everything. Okay, so that's the canonical example. Now I have one more very important thing to say and illustrate before we get a little break. The definition, as I've written it, depends heavily on both the prior and the decision problem. I've shown you these, I've mentioned these extreme examples, that it's actually true for all decision problems. This one is true for all decision problems. This one is true for all decision problems. It happens to be the case. That's extremely rare, extremely difficult. I think the recitation in the afternoon asks you to try to work some examples and see.
You want to say that there are substitutes for all decision problems, and the second case is complement for all decision problems.
Excuse me, the XOR example are complements for all decision problems. Thank you. This example are substitutes for all decision problems. Let's illustrate the XOR one. Why is that the case? Well, any decision problem is a convex function, is represented as a convex function. Any convex function I try to draw, well, the marginal value of the first signal is going to be 0. And the marginal value of the second signal is going to be non-negative. I mean, if you have a linear function, so your decision problem is I always, take an umbrella, doesn't matter. The only thing I can do is take an umbrella. Then your value is 0 all the time, and this inequality is weakly satisfied. But no matter what convex function you try to draw, this example will be complements. Now, as soon as I start changing this, this can change drastically. So I'm not going to go down the road of saying, let's look at the class of things that are always signals for every decision problem, or let's look at the class of signals that are always complements for every decision problem. My understanding of those classes is actually pretty limited. It'd be really cool to have more investigation into those, but it's very, very restrictive. what are we going to do when we come back? We got all the way to here. That's about what I was expecting. We're going to talk about using the value of information to try to procure it in a sort of market type setting. And then we're going to talk about how we can modify the whole framework and mentality that we're taking approach to this, where information is represented as data. All right, so see you after the break. Hi, everyone. Welcome back. Let me recap the narrative. Narrative is, how does information work? What happens when we get information as Bayesian rational agents that we all are? How does that give rise to value of information, which we've seen earlier this week already? And as part of value of information, I'm extending it to talk about substitutes and complements. And then next, we'll talk about procuring information, or sort of a marketplace for information in a sense. And then we'll go back and we'll talk about this in the context of data. And yeah, we'll do the same narrative. We'll definitely need to skip a little bit of stuff that I was optimistically putting in, and we can talk about it after. There'll be a little less machine learning-y stuff than I'd love to do, but some. All right, how are we doing? All right, good, good, good. Okay, I want to say a couple more things about substitutes. So I have this intuitive example I want to think about. Signal A is, does the dish that I'm considering buying have chunks of meat in it? Signal B is, was the dish cooked in a meat broth? These are the two things I consider when I go to buy food. Now for me, I'm going to say these signals are substitutes because they're highly correlated, and if you just tell me one of these, I don't really need to know the other one to make my decision of whether to get the food or not. But you could imagine, I haven't written any math, a vegetarian, someone who does not eat meat, for whom these signals are complements, in the sense that they can't decide about whether to eat the dish or not unless they know both. Right? They need to know both of these pieces of information. One piece of information is a little helpful, maybe, but it's not really going to let them make the decision they need to make. So this is trying to illustrate an example of the principle that I mentioned out loud and will write on the board. The definition of substitutes depends heavily on both the information structure and on you. Okay? And maybe you could try to remove the dependence on you and think about, okay, just the information structure. What's the value look like? And Jason had this cool idea of max value of information that didn't depend on you're optimizing over a class of decision problems. You could try to do the same thing here. I think it'd be really cool. That can definitely lead to some interesting work. But you're going to rule out examples like this where the same information structure for two different people has really different meanings, economic meanings. Okay, so I wanted to say that. And I wanted to, just because I like the substitutes concept a lot, give you some quick interpretations of value of information and substitutes that I think are really nice mathematically. The first interpretation is one we've already seen, which is diminishing marginal value of information. Okay. The more stuff I know, the less marginal value this piece of information has to me. I know a lot, I don't need to know this anymore. Yeah, let's consider a second one though. And to do that, let's consider the log scoring rule. S of qy is log q of y. We've talked a bit about this yesterday, I believe. And the expected score, S of qq, which is g, that convex function, is sum over y, q of y log q of y, which is what well-known function?
Minus entropy.
Minus of Shannon entropy. Shannon entropy is this concave function. This is the negation of it, a convex function. And if we look at marginal value of information, in this case, we actually get a formula that we talked about before. So the value of A, first of all, is going to be the negative of Shannon entropy of Y given A. Good. So as A makes you more and more certain about Y, the entropy in Y goes down, the negative of it goes up. The more certain you are, the happier you are, the higher your value. If A provides you lots of information about Y, it has very high value to you. So that's the net value of A. The marginal value, sorry, yeah, that's not the, well, okay. Yeah.
Sorry, next question. Why you are using only decision problems that are coming from proper scoring rule, just for me to
yes.
anticipate, to focus.
It's It's not going to be super important that my examples are coming from proper scoring rules as opposed to other decision problems. That's just what I'm familiar with. And in this case, it leads to something I can say is related to other concepts. Yeah, so I'm going to skip to the punchline. The punchline, okay, if the value of a signal is how many bits of information, well, basically remain, the marginal value is how many bits of information do you learn? So what's the condition? What's the entropy of Y before you are going to learn A, and what's the conditional entropy of Y given that you learn A? That's the marginal value of A. So interpretation 2 of interpretation of value is information, bits of information. Substitutes is diminishing marginal bits of information. We could call it bits or amount of information. And for the log scoring rule, this is literally true for Shannon's definition of information.
So what was the formula for value?
So marginal, should I write marginal value?
A, what was the formula?
V, yes, thank you. Let's recall. Capital VU of A is the expected value I have in my decision problem U. Excuse me, here U is the log scoring rule. The expected value I have in my decision problem for acting on the information in A, in expectation before I have seen A. And it's this. So the marginal value is, if you write it out, turns out to be exactly how many bits of uncertainty I had about Y were eliminated when I learn A on average. Kind of cool. I3, I'm going to go back to something else that we wrote. We wrote the following. For any scoring rule, the difference in score, expected score, from reporting something true belief and misreporting is a Bregman divergence. You can leverage this to show that marginal value of information for any scoring rule now, let's say V of A over the prior, is going to be the expected Bregman divergence between your posterior and the prior. For example, there's a quadratic scoring rule. S of QY is, I like this version, Q minus delta Y squared, minus. Okay, there's a quadratic scoring rule, which is basically your distance from, you could do 1 minus as well, your distance from, your Euclidean distance squared from the true answer. This is the generalization of squared error to higher dimensions. The Bregman divergence, so the convex function associated with this is 2 norm squared. You're doing some of this in your recitation. By the way, your recitation leader is Robin, who is here. Please wave, thank you. So you know who to look for. The Bregman divergence is Euclidean distance squared as well. So here the marginal value of information is literally the distance that it changes your belief. And so substitutes are this idea of diminishing change in belief. So if I literally look at how much does my belief change measured in a distance, if I know lots of things, learning this changes my belief less. If you think about the XOR example, we had that here. Learning one thing changed my belief not at all. Learning the second thing changed my belief completely. Highly complementary. Highly complementary. Whereas in this example, learning one thing changed my belief, but learning the second thing changed my belief not at all. Highly substitutable. So I3 is diminishing marginal change in belief on learning information. Okay, just some kind of flavor background for value of information and these definitions. Let's talk about, we're getting very close to data. We're going to talk about procuring Bayesian information, but it's going to be closer to data than you might think. I think we're getting really familiar with all of this, and we can turn it around now. There's room. Okay, so I'm going to describe this concept of scoring rule prediction markets, which wasn't defined with all of this stuff we've talked about really in mind necessarily, but is very compatible, highly compatible with it all. So prediction market, is this going to be visible? Is a game we set up that will end up procuring or revealing information that strategic agents hold. So we'll have n agents with signals, and we have a joint prior. Let's write the signals as A1 to AN now. So we have a joint prior on Y and the signals, where AN is the nth player's signal. A1 is the first player's signal. Okay, so all these signals are jointly distributed, they're correlated with each other, and with Y, the thing that we want to predict. These are private signals, so the only one who sees AI is player I. They do a Bayesian update, they have a posterior. Others see their signal, but they don't see each other's signals. I'm not going to actually analyze equilibria of this game, but I will set it up. And we can define a scoring rule market. For
Was it yesterday course?
no, we didn't.
Prediction market, is it yesterday course or something?
No. So yesterday, the main term of what we did was peer prediction.
Three predictions.
Everything yesterday was no ground truth. Everything today, we get to observe the ground truth and use it to score people. That's a good distinction. So scoring rule-based market given S. This is defined by Hansen in 2003. There are references in my notes. You initialize a prediction, and the agents are going to come and update the prediction. And they'll get paid with a proper scoring rule for how good their predictions are. So start with P0, which is just some initial distribution. Maybe the market maker knows the prior and they set P0 equal to the prior P. Maybe they don't know the prior and they just do the uniform distribution. Okay, in rounds T equals 1 to capital T, agent T arrives, and they update to PT. What do I mean by update? This is going to be a global prediction that everybody sees, and each agent is going to take turns changing it to what they think the right prediction should be. So this is an updating the global prediction, or so I don't want to use this word update because it's like a Bayesian update, so let's just say they report PT. But when they make this report, it's global. So we have a shared prediction sitting there. Agent T arrives and they change it. Agent T plus 1 arrives and maybe they change it back. I don't know. And this continues.
What does this mean, reports? To whom?
To the mechanism. And it's global.
There's a mechanism designer
Yeah.
There is some
Yes.
someone,
Yes. That is.
central entity,
Yes.
and each one can and report at INT some prior
Yes.
on the offer.
Yeah. Well, hopefully it's a posterior.
Posterior.
Yes. And this is globally visible. Everybody sees all these reports. And the most recent report is the market state, and it's like the current prediction that the market is making. What you hope is happening is information is being aggregated, right? Someone comes and they say, well, I think it's over here. Someone comes and they say, well, I think it's over here. After that happens a while, you kind of hope things are settling down, and people are not making big changes because a lot of people before them have said this thing, and they've updated on that information. Hopefully.
I don't need to see the whole history. I just need to see the last days.
You might or might not need to see the whole history to do a good Bayesian update, I guess. So for simplicity, let's suppose you do see the whole history. It probably doesn't matter. Most of it, I wouldn't worry about the distinction today, for sure. Okay, the market ends.
Agents know pi.
Thank you. Pi is common knowledge of the agents, not known to the mechanism designer. Maybe the mechanism designer knows the prior P on Y. Maybe they don't even know that. And again, I won't actually do the game theory, but it's good to define the game correctly. All right, so this just happens a bunch of times and it stops. And then we're going to do payoffs. When it stops, after it stops, we're going to observe an outcome y equals little y.
Is it stopping moment random or?
Generally, I'll say it's fixed in advance. So,
Capital T, some capital T.
yeah, let me actually clarify one thing. Let's suppose every agent is assigned certain times at which they arrive, possibly multiple, that's fixed in advance. So you know that you're participating on round, maybe it's just one agent 1 to n, 1 to n, 1 to n. Okay, stop after 3n rounds.
So the sequence of reports is known.
Yes. So in a theoretical model, now people run these things in the real world. They look a little different. I'll talk about it. And there, the sequence is not fixed and known. People can arrive whenever they want. Yeah. Yeah, this is very online, though. Stops, we observe y equals y, and the payoff for report T is a proper scoring rule of that report PT, but minus the score for the previous day's report. So what I mean by this is if you participated on 4 different rounds, you'll get this payoff for the first round and this payoff for the other round and this payoff. And each round you participated, you'll get this payoff. Now, for simplicity, it makes a lot of sense to consider a game where we only participate once each. But in a real world, it makes sense to model people can come back and participate multiple times, among other modeling choices. That's a... Yeah. Yeah, so for now, let's just think that t equals n, and the agent 1 arrives, agent 2 arrives, agent n arrives, and we stop. We don't... I'll mention what happens beyond if that's not the case. Yeah.
What's the intuition behind getting a payoff related to what the previous player did?
Yeah, good. So let's think about this.
Additional information you give, I guess.
Yeah. So it's...
And also, I think you have here you maximize on PT, and since it's truthful to reveal the information, everybody will be truthful if everybody before was truthful. I'm guessing, but I'm not
Okay.
completely...
You've covered 2 of my bullet points. What is the third?
I don't know. The third one is that it may convert to something that
Yeah, that's pretty much it. This is why he's the big boss.
Can you see that?
Okay. So, first observation: if you arrive only once, which let's suppose that happens, this is a truthful mechanism. What do I mean by truthful? It's a little complicated. I'll say it out loud. You maximize expected utility by, at the moment you arrive, reporting your current posterior belief. And you may have Bayesian updated on things that happened prior in the market, as well as your private signal. But you always maximize your utility by reporting your current posterior belief. So that's what I mean by truthful. Yes. You maximize expected utility, net utility in the game, by reporting current posterior belief. Why is this true? It was mentioned. You're paid with two, well, at time t, and let's just, you arrive only once, so you're paid with two things, plus the score of your prediction that you made, minus the proper score of the previous prediction, something that you have no control over. The expected value of this from your perspective is constant regardless of what you do, and this is a proper scoring rule. The definition of a proper is truthful. You maximize expected score by being truthful.
So I guess the point is if you arrive, you can participate a few times, you might lose truthfulness.
Yes, so if you can participate a few times, it gets ugly, and we're not going to get too far into it. But you will have a recitation question that's kind of one of the key questions that relates to that.
But the question
I'll
is how
I'll
you
mention.
maximize your utility in that case. It should be kind of diffusing your information.
Yeah,
Variation, something.
very complex. Yeah.
Like your value is symbolic or something like this?
Okay. No, I'm gonna say what you said in a bit. Yeah. Yeah, that's exactly right. The second bullet point, which again, well, yeah, okay. Actually, sub bullet point. What is your payment and expectation? Expected payment at t.
Sorry,
Yes.
question.
No, please.
Even if PT minus 1 was live,
Yeah.
I don't care because it has nothing to do with my payoff. So I
Yeah.
can still report my belief given that it's a scoring rule. That's the argument.
Yes, yes. The argument is I might be sad about PT minus 1, or I might be happy that it's a really bad prediction and I'm going to get a big bonus. But either way,
I don't control it.
I can't control it. My expected payment, okay. Optimistically, the expected payment at time t. Well, let's consider this case that Jason mentioned. Let's have agent I arrive at time I. Agent 1, agent 2, and then let's stop after they all arrive. So optimistically, the expected payment is, well, the expected utility of this acting in this decision problem with this information, which is your posterior, compared to acting with this information, which is the posterior of the person before you. So it's going to look like, optimistically, the value, expected value in this decision problem, S, of having access to all the signals up to time t, minus the value of having only the signals up to time t minus 1. Okay. And actually, okay, if everyone only arrives once, they're truthful, so they do indeed report their true belief. And under some conditions, they can conduct these Bayesian updates correctly. And they do Bayesian update correctly, and this actually does happen. So this is not even that optimistic once we've fixed the arrival order in this way.
Doesn't this assume that agent I has access to the signal realizations of all?
Good, so this is part of the optimistically. Optimistically, when player 1 updates to P1, I see that and I infer the realization of their signal, little a1. And as player 2, I now have both A1 and I have my private signal A2. It's a little optimistic because there could be multiple signals that cause them to make the same report. Generally, I'll assume that away.
So your example of XOR is one where you learn nothing.
XOR is an example where my optimism fails in different ways. But one of those is Alice, the player A, comes and they say, okay, the previous prior was 0.5. I also believe 0.5. Player B says, I learned nothing. I also learned 0.5. You can have them play this game all day and they'll never converge. They converged on the first step to 0.5. They'll never converge to the truth. Yeah, and actually that's the content of Ostrovsky's 2013 paper on information aggregation in markets, It's kind of when can you design a richer class of securities or things you're predicting over to make sure that information gets revealed by prices.
Can you just have the agent also report the zero signal realization?
Yeah, so you could imagine that. It's kind of hard to make that really truthful for reasons we talked about yesterday, where like I'm reporting a signal realization, but the mechanism doesn't know how that relates to their posterior if they don't know pi. But you can imagine, I mean, you can imagine a prediction market which exists with like a discussion board, right? And someone places a huge bet, and then they go on the board and they explain their reasoning, and that's like reporting their signal. And they might actually want to do that because now that they bet, they want people to have aggregate that information.
So the motivation behind this is designing a platform where people are incentivized to reveal their information as fast as possible, truthfully.
So this can be used in a few different ways, but they're all pretty similar to what you said, which is
How should I think?
one way to think about this is procuring information. That's not normally exactly how we say it, but I like procuring information. I am a mechanism designer. I want to know about why. Why is extremely important to me. I don't know about why, but lots of people in the world do. I create a market, and I say, I have a lot of money to pay people in this prediction market. Come and predict. And then eventually, hopefully, they'll converge to a prediction where, okay, so I should have said, PT will be the posterior, well, indeed, P sub A1 up to AT. And at the end, A1 up to AN. All of the information will be aggregated of the best possible prediction. So I've procured that information for myself. In fact, if I'm acting with a decision problem, I have a utility function. I could even base the scoring rule on my utility function so that it's incentivizing the information that I care about.
But the payoff will be given at the end.
The payoff is not given until I observe why. Yeah.
Why? But why then it's publicly observed by everybody?
Yeah, let's suppose. So they're not worried about me lying about why. Now, people run prediction markets on blockchains, and there, even if y is publicly observed, the y that gets into the blockchain for the payoff functions can be manipulated, and you have to worry about this. Yeah.
So can you give us a real example now?
Yeah, so political prediction market, well, it's not usually formatted this way, and I'm going to talk about.
Would be the outcome of the election?
Yes, so multiple candidates are running for president of some wild, crazy country, and we want to predict which one will win, and the probability is the probability of, say, the Democratic candidate winning. And
So do you think
yeah.
But this can be negative. This can be negative. So
Yeah.
Do you think
Yeah.
the large bet on Trump swung the election?
I have no idea about that, but yeah, there was this.
Cameras are rolling, though.
Yeah, I have no idea about that, but it is a very interesting story because apparently,
You're gonna tell the story?
there's I think blockchain-based prediction market for the United States election. The U.S. is a country that does elections, and
You're on camera about it.
there was this very large change in the prediction market probabilities leading up to the election, and it turned out to come from one particular person betting very heavily. And people wondered if it was for reasons of trying to, not actually changing a belief, but just trying to influence public sentiment, like make people believe that the probabilities had changed. But my understanding is that that person said they actually conducted a lot of research and even paid for pollsters to go to locations and try to poll better than the publicly available polls. And they ended up making a ton of money.
Yeah, he bet
And-
on Trump.
Yeah, that one.
Like millions of dollars.
Yeah, I think tens of millions. Maybe the profit wasn't tens of millions, but the position. And I don't want to say in the front of a camera that that's a success story for prediction markets. But the format of a success story for prediction markets would be, I want to procure information about something that really, really matters to me. And I just post a market. And somebody out there who's savvy and know-how and has a very large bankroll uses some of that money to collect information and go out and get the information, and they incorporate it into the market, and we get good predictions. Is that what happened? In this case, I don't know, but it has aspects of the story that I would love to see happen in the future.
So
Yeah.
my question is this prediction better than Paul's classical Paul prediction? When
like
you don't
peer.
pay money and just you call people and you ask them what they
The Clinton,
Okay, so
do we have a solution?
the Clinton, Trump.
right, so it's hard to answer the question of whether these perform better at predicting like political events than other methods of forecasting. My understanding is that generally studies don't find this to be worse than something like the polling and trying to readjust for the polls, and sometimes find these to be better, but generally don't find them to be worse. One reason it's difficult is like these big political elections only happen every few years, and if you get some weird events,
But there are other places where we bet. And we
yeah, so you could look at
Other
sports.
sports even.
You could look at like sports gambling, which really isn't all that different from this. I think in a certain mathematical technical sense, but I don't know if they have good things to compare to. Like in those settings, the gambling markets are so well known that all the information is kind of linked to each other.
But like
Yeah.
famously in the Clinton-Trump election,
Well, people said prediction markets got it wrong, right? Is that what you're?
I thought
see.
like 458 or whatever that number. 438.
Yeah, Nate Silver's predictions, but he didn't use straight prediction markets. I think he used simulations
Yeah, I thought it was a success story for prediction.
because they were put a higher probability on the outcome than
the
other
polling
experts.
did. Yeah,
Yeah, but
polling was even worse.
yeah, but you have this problem where like if you observe just a few events, like someone who's guessing each time can get lucky, or a prediction market can get lucky, and it's not statistically significant. So I hesitate to say, but if you have a very large market with lots of money involved, there are incentive reasons to believe the prices will be correct. All right, let's do a little bit more of this and then go back to math.
I just want to say, the stock market is a good example of like a prediction market.
So there are a lot of aspects and similarities in financial markets, and like Ostrovsky's paper that I mentioned deals with both a prediction market and a financial market. And information is hopefully being aggregated in a financial market by buying and selling and reviewing, do I believe this is going to be good in the future or not? Yeah.
So from the perspective of the mechanism in China, is it any difference to make each agent report globally? Or reporting the private little mechanism in China and not making them update?
Good, yes. So let me also compare. So imagine if we kept this private, and let's actually compare to something else. Like, so there are things called wagering mechanisms in our community's literature. All the agents report simultaneously, privately probabilities, and then we see what happens when we reward them. The problem is aggregating these predictions into one prediction. If I don't know pi, it's difficult. I can go really wrong. And so by making it global, I'm making the agents do the Bayesian updating for me. And it's hard to do that without them.
So it's a question about knowing or not knowing the prior, the pi, the joint distribution.
Yeah.
And if I know it,
Yeah.
it's basically equivalent to make them.
Yeah. So if the designer knows it, maybe they just, you can even just collect the signals and do something like pure prediction, but even better, or just proper scoring rules. Yeah. Yes.
So I have two modeling questions.
Okay.
Question number one is, how realistic is the assumption that everyone knows the prior?
Yeah.
And the ability to construct an oracle that they successfully do PT, they report PT?
Good. Okay. So how realistic is it that they know the prior and they can do all this Bayesian updating? Certainly in like a financial market, these are extremely large objects. I don't want to take a stand on that. I think there's problems with this exact model. Actually, today I'm going to focus much less on that and more on the format of this and why the format makes sense, with this being the first kind of indication that the format makes sense because at least it works in theory. And then is it the type of theory that is robust in practice is an interesting question. Yeah.
So my second modeling question was, going back to your prediction market example, why is I don't see how the payoff matches the example.
Which example? You mean the person who bet a lot of money and so let's say the probabilities before they started betting were 0.5, and they bet. Imagine they made one big bet and they predicted 0.6, and imagine that this scoring rule is something like 1,000 times or 1 million times the quadratic score. So you moved it from 0.5 to 0.6, and then the outcome y was 1. the quadratic score of 0.6 minus quadratic score of 0.5 times a million, or whatever would have been. And actually, the prediction market might have worked that way, but it probably didn't work exactly like that. The quadratic score is not a great scoring rule to use because of what Jason said 2 days ago about peer grading, right? If you improve the prediction a little bit, your utility, I mean, you can try to scale up these numbers so that they're very, very large, but then you're paying a lot of money in other cases that you don't really want to. So design of the scoring rule to acquire information, you can think about the principles that Jason talked about for optimizing scoring rules, and they make a lot of sense here too. Please.
There seems to me to be a distinction between like the sports betting type of market where you have information but you can't influence the outcome versus elections where you can influence the outcome. And maybe you can just say that your personal vote is just like some tiny amount of like information that goes into your posterior, but then you can also condition like your vote if there's 3 candidates on the outcome of the market that you observe, because maybe you would vote for your most preferred candidate, but you see they're not going to win, so you change. So are these models the same type of prediction market, or is there some distinction?
This is definitely assuming that you do not have influence on why. Everything you said is super interesting, and I don't want to get into it today because it's easy to get me distracted. I'd like to pause discussions except for a kind of clarification to continue for now, and questions are good, but I still have some things that Rita said that I haven't written yet, I believe. I think, these were the key ones. Agents arrive only once, it's truthful. And if we combine that with this formula, like assuming that they can do the Bayesian update, then the payment is going to be the value of your information, the marginal value of your information. Another two, this leads to the observation that, what's the total payment? It's a telescoping sum, okay? So I have S of P1 minus S of P0 plus S of P2 minus S of P1. All right, so the total payment is the score of the final prediction minus the score of the initial prediction. And in expectation, it should be the value of all of the signals minus the value of having no information. That would be if I predicted the prior to start with. Okay, so I've procured information and I've paid its value for it. Okay, now a much better realistic model, this relates to the example, would be agents initially don't have information and they have a cost of effort to acquire that information. I don't think that's really been done in the prediction market context. But so exactly, again, optimization of scoring rules is an opportunity for this context, I think. Grant Schoenebeck might have something related to this.
In this example, in this game, let's say in this context, you want to have the one having the maximal variation. Because
Right. So you can most
each time you want this function that jump a lot, but I don't know which one.
Yeah. Right. So one observation is the V-shaped functions that Jason derived for us that optimize the value of information. They're really optimizing the value of the first signal, of a signal. But once for example, let's say we know, once we know, for example, that the probability is definitely above 0.5, additional information has no value. So we don't quite want to do that, but we can use the principles, to design something better. Might be complicated, great, like open direction. I don't think there's much there. Perfect.
Is it making sense to have kind of random function S? To add a layer, you have Y and some with some the function is chosen at random.
Yeah.
But not revealed to the people. It is the blockchain. But this function will maximize the variation, let's say.
Yeah, I think one issue is if you draw S at random and pay people with the realization, their expected payment is the expected value, and that traces out some convex function, which is a scoring rule,
Yeah.
and you could have paid them deterministically with that, and their expected utility would be the same.
Then if you pick the asset adversarial, let's say like an online learning kind of.
Yeah, you could try to pick it in a way that, but then if it depends on the
Specify
p's, yeah,
variation, something like that, so that we don't have this.
yeah,
I have many like this, and one of them will be relied, they don't know it.
right. But like
something like that.
Mhm. But like an expectation over a bunch of V-shaped scoring rules could end up looking like the quadratic or something. Well, actually, it can look like anything according to the exercises. Yeah, it's great to think about. I'll continue, but yeah.
So the central agent does not have infinite amount of money. They have a finite budget, and according to the realizations that they don't control over, they might basically they might get scores, and they might have committed to budget. They might go over budget.
Yes. Okay. We're going to talk about this, about budget.
Oh, okay.
Most of it is going to be in your exercises or their exercises. Yes. First, no, you know what? I want to say that, well, okay. An exercise is going to be how much money can you lose and what restriction should you place on your scoring rule or on the convex function g so that you don't lose too much money as the designer. And okay, this formula is getting you pretty far there, so you just have to think about properties of proper scoring rules and it'll be good. But the answer is that yes, you can bound for any constant. Of course, if you make it really small, you're not incentivizing people to procure information, so there's a trade-off. But okay, I want to say one more thing. So theorem, let t be greater than n. People can arrive multiple times now. It's going to be informal because I won't define everything. The participants, quote unquote, rush to provide information and are truthful at every opportunity. They always provide all of their information when they have an opportunity to trade. This nice property happens if and only if the signals are substitutes. Now, it's not quite the definition of substitutes I gave there, because that definition doesn't think at all about garblings. And one thing you can do in a prediction market is garble and reveal less information than you actually have. And so, for example, if signals are complements, you might do this. You might say, okay, I'll reveal a little bit, but I'll wait until some information is revealed. And when I combine it with my information, I can make a really big move and make a lot of money later. If signals are substitutes, you don't want to do that. You're going to prove a version of this where an agent gets to decide when they want to participate. And the idea is going to be to use the definition of substitutes. And yeah, that'll be the recitation. All right, we get to talk about data now.
So for complement, it should be the opposite.
Once we're done.
Reveal at the end.
For complements, and it's more complicated for an interesting reason, but for complements, the opposite. What do I mean? Also, this is like in a Bayes-Nash equilibrium. So any Bayes-Nash equilibrium has this property. Yeah. For complements, I could prove for any like perfect Bayesian equilibrium or something. Yeah.
Maybe the question doesn't make sense in this context, but this seems to be the there's some learning when you're reporting truthfully.
Yes.
Does this is guaranteed to converge to the place it should go?
So
or it drift away for some.
yeah, so from a Bayesian perspective, what should happen in Bayesian world is we get the posterior condition on A1, we get the posterior condition on A1 and A2, and at time n, we get the posterior condition on all signals, and anyone else who arrives says, I have nothing more to add, and I won't make any changes anymore in the Bayesian world.
If we're truthful, we converge to what we should be converging.
Yeah. If we're truthful and there's this issue of like, can you interpret a trade as, can you find the outcome of their signal from their trade and do a Bayesian update properly? Yeah. Okay, actually there is one more thing I want to mention. Well, this is getting to data. I'll try to make this one brief, but very important. So normally a prediction market looks more like a market. And I want to mention that really quickly with an analogous setup. So as a market, we have the following setup, let's say from scratch. This is the design of a mechanism, excuse me. So I have n quote unquote securities. No, I don't. I have size of y securities. And their format is they pay off 1 if y happens. Okay. And we're going to let people buy and sell these securities. So if you think that an outcome y is very likely, you'll buy a bunch of shares in that security. And when y happens, all of those shares will pay you out $1. And now we're going to let people trade these securities with the center market maker. It's called an automated market maker. You trade with the market maker, not with each other. So how do we do that? In rounds.
You can buy or you can also sell.
And you can sell. And you can even short sell, so I can buy negative shares. And then if the outcome happens, I have to pay. Yeah. At least in the theoretical setup. Okay, so in rounds, T arrives and demands a bundle. Let's say RT, which is just some number in R to the Y. Okay, this is how many shares of each security they want to buy. And I'm going to charge them a price right now, which is going to be some PT dot RT dot product. I guess I've been using inner product notation. Sorry, let me say this. I initialize with P0. What's P0 and what is PT? Well, sorry, let's just say, PT minus 1, and then I update my prices to PT. Okay, so PT is a vector of prices. Your payment is the sum over the coordinates y of the price for that security times the amount that you demanded. Is that clear? What are these prices? Well, exactly one of these things is going to happen. The prices should be non-negative and sum to 1. That's sort of what a reasonable price would be. Because in expectation, exactly 1 unit of payoff will happen.
Only one is realized when you say y security?
Yes, only y, so what, this is a...
If y happens, the other doesn't happen.
Yes, otherwise 0. Yeah, yes, the outcomes, the random variable y will take 1... Yeah, yes, yeah, excuse me. So the random variable y will take 1 realization out of these possibilities. When it happens, that security pays off 1, but the rest pay off 0. The prices of the securities should all be non-negative and should sum up to 1. Because basically your expected payoff from a security is the probability that that event happens. And so hopefully these prices reflect the probability that the event happens. Okay, so you just do this all the time. You have some algorithm that's deciding based on these bundles, how should I update my prices? Imagine this for a while. Don't worry about how it connects to this yet, quite yet. Okay, and the last thing I'll say at the end, the last thing I need to define this is that y occurs and t gets paid RT of y. Or another way you could write this if you wanted to, which I kind of do, is delta y dot product RT, or inner product RT. That's just saying if you bought this many shares of outcome y, then this is what you get paid out. That's what I define.
So I only at the end of time, I pay everybody before. It's a capital T.
Yes, I wait till the end of time, and then I see. So people are now paying me along the way.
They bet before.
They pay me to make their bets, but at the end of time. And I want to mention that, okay, so how much does my spend as the mechanism designer? Well, I'm spending kind of the sum over time of PT dot RT. And then, no, I'm sorry. I'm getting paid that amount. So I'll make that negative in my spend. but I have to pay sum over the time steps, RT, of the y that actually happens. And in the worst case, what I might be worried about, a sort of worst case spend.
I should buy them at one. Why? Sorry.
Yes.
As I understand, this is what I get from the others, because I should pay them for the one on the left. And what's
Good.
here?
This is the payouts I do at the end. For every agent, I have to pay them out for the shares that they bought.
And why I should. So this is minus, and then this one is what I.
Plus, let's forget the max. So what do I, oh no, you're right. I'm sorry. This is minus as well. Is that?
Okay, but what is this minus?
Is that right?
I should buy it or something like that?
Yeah, I'm sorry. I went too fast. Okay. It's a plus. I'm spending this. I'm paying for every arrival T. They bought this bundle RT of Y, and now I have to pay. They bought a bundle RT, and when Y happens, I have to pay them RT of Y. That's what these securities mean. So if they bought,
they give me RT of Y.
no, they. Let me just recap it from the beginning.
Okay.
Yeah, no worries. So let's say that capital Y is. We'll do the political example. So candidate X, candidate Y, candidate. Whatever, I don't care. T arrives and they say, I want 5 shares for candidate X and nothing for candidate Y.
Okay.
I tell them, okay, the current prices are 60 cents for candidate X, 40 cents for candidate Y.
Okay.
Your total payment is 60 cents times 5 shares. Pay me that. Okay. And then I also update my prices for later. Okay. So I've been collecting all these payments. Mm-hmm. I'm going to make that negative in the amount I spend. The sum of the payments I've collected. I'm not going to deeply mathematically analyze these. But I'm trying to be precise. At the end, Y occurs, and that person, let's say that the first candidate does win. They bought 5 shares. I need to pay them $5. In total, I need to pay the sum over all time steps of the number of shares the person bought in the candidate that wins. Now, if I'm thinking about I'm waiting for the news to come out who won the election. The worst case there would be the max over Y, RT of Y. I'm hoping this is looking very similar to something. So let me ask, who has seen online no regret learning? Come on. Who was here Monday? The only person who is allowed to not raise their hand is Rachel, who I know should raise her hand. What happened in the first setup on Monday? Every round we had to pick an action, and it turned out a good way to do that was to pick a distribution over actions PT minus 1, let's say. And then we got a vector of possible losses. I don't think it was phrased quite this way, so it will look a little different. We got a vector of possible losses if we had taken each action, and our expected loss would be the dot product. At the end, we could look at our algorithm's expected loss, and we could compare that to the worst case, the best action in hindsight, which is sort of the maximum sum of a column of these. And so actually, the format of regret is the same as the format of your spend here, which is kind of wild. This is kind of pointed out in a paper around 2011 of Abernethy, Chen, Wortman, Vaughan. So this market is really an online learning problem where the information people are providing is contained in their demand bundles. And this is data. We're getting toward data. We're going to do more with data. This is some data, and we have to learn from that data how to set our prices. But it's a prediction market. I mean, we're using these to set these prices P. And if we have a good algorithm, hopefully this P does indeed converge to a sort of posterior belief of everybody, conditioned on all their information, and they no longer want to buy or sell anything, and it starts getting stable because everyone agrees. And what's wild, in my opinion, is that for certain strategies of algorithm of how to set prices, these will actually be the same in a formal way that we don't have time to get into and can be captured informally. The sequence of P's will be the same for the same sort of traders with the same beliefs and the same, they're optimizing their utility.
So you're saying there's a way to update PT such that
There's-
it looks like the
There is so for any scoring rule, there is an algorithm for updating PT so that it looks, so that the same thing happens in both worlds.
and that thing gets you lower.
So not necessarily. So we'll talk about regret in a moment. But let me give an example. Who's heard of the exponential weights algorithm? Thank you. We're almost all of us were here Monday. Something very similar to that, basically the same algorithm, is an example of what's called follow the regularized leader, which has this convex function regularizer. For that algorithm, it happens to be entropy, or the negative of Shannon entropy, and you kind of minimize, you choose P to sort of minimize your expected loss or your average loss so far, but with this regularizer of entropy. Multiplicative weights, that algorithm is the same as doing this with the log scoring rule. You'll get the same. You'll get this algorithm from the log scoring rule. And in markets, this is called LMSR for log market scoring rules. So if you look at prediction markets, you'll see this. Super cool. So it has to do with a convex duality, duality between convex functions. But we don't have time to get into it. But you can do, so if you do a quadratic score, you're basically going to get gradient descent on the right side, and so on. And now some of these will have low regret and some won't. There's one important difference here which I don't want to get deep into. What you do in the prediction market is you don't actually charge this dot product. What you do is you kind of charge this instantaneously. So imagine that the person is starting to buy their 5 shares. Currently, my prices are 0.6, 0.4. As they buy a little bit, I start raising my price. I start raising my price, and by the time they've bought 5 shares, my price has continuously increased to what it will be at the end of the update. So the design of the prediction market was going to be equivalent to this if we were allowed to do something a little bit different here. And that difference allows you to get bounded budget, bounded spend in settings where you can't necessarily like bound the regret. So there's a slight difference there. Not super important to the intuition though. Okay, we're going to talk more about data, but I'll recap. Yeah. So let's see, prediction markets. In hindsight, it's kind of the thing you have to do if you want to pay exactly the value of the data for the data. Right, because of these properties we talked about, the total payment ends up being the value of all the information you got. I said data, I should really say signals or Bayesian information. They're kind of the thing you have to do. They have to be based on convex functions, but they correspond to these learning algorithms, which I think is super cool, where again, a trader's update is just their demand. They're just saying, look, based on what I believe, I want this many shares of this many shares of that, and so on. And of course, for online learning, they should really be bounded in a 0, 1, but excuse me. Based on that data, you update, and you're doing the same thing as the prediction market. You're aggregating information, but in a sort of data-dependent way. And you have an algorithm that's running on data, but it's aggregating the information. Okay, so we're going to extend that idea to machine learning contexts. Yes, please.
There's one funky thing that seems to have happened where on the left side you have the agents have these knowledge of the prior and their coming up with a PT based on the agent update, but on the right, the designer or the market maker is coming up with a PT solely by looking at the reports. Like, how did this switch?
Yes. So what's going to happen is in the equivalence is the market maker will publish their algorithm, and an agent who believes PT is going to buy just enough so that the algorithm updates to PT and stops there, because that will maximize their utility. Yeah. But of course, you know, this is sort of a much more robust idea, right? That we don't need assumptions on behavior or anything. We don't need any assumptions at all, and we just have a regret bound. But yeah.
Actually, if you have a market, you by selling or buying, you say how much the price for you should be. So you clarify the probabilities, and you report those truthfully. So it's
yes. A simplification of this could be the only thing people say is buy or sell. They come in and they say, the price should be higher, I'm buying. Exactly. The price should be lower, I'm selling. What does gradient descent do, right? I should go left or I should go right. I mean, not quite, but not in high dimensions. Yeah, and that reminds me of something I wanted to say. I wanted to mention Aumann. So imagine a conversation between Bayesians about the weather tomorrow, right? As Bayesians often do, they discuss the weather. Initially, each Bayesian has a belief in their head, and they have a signal in their head about the weather tomorrow, and they'll say something, and it will reveal some information, and the other person will update, and that person will say something back, as good Bayesians do in a conversation, and the first person will update, and so on. And you're going to have a sequence of information revelations, and it's really not that different from, you can model that in the same way as you could model these prices changing. Right? Especially if you had a binary event here, it's just going up or down. So any conversation between Bayesians has this, it'll look like a martingale. It has all these same properties. One thing Aumann noted is that if the Bayesians keep talking, they'll have to eventually agree, which is analogous to the market converging to a price. Right? One question, which I also wanted to, yeah. So far, are you asking if I'm familiar?
Agree to disagree doesn't have this. It was proved later by Giannakopoulos and Polemarchus.
Yeah. So
discussion will lead to agree to disagree. They tend to end up by agreeing. That's what
Yes. Yeah. Sorry. So Aumann said you cannot agree to disagree. If you talk long enough, you'll end up in agreement. And people have done this in a market context. But one interesting question is, so that's just kind of an interesting side note, but one interesting question that I looked at with collaborators is, just because you agree doesn't mean that you're correct. This has come up a few times. Doesn't mean you're perfectly accurate. In the XOR example, you agree that I believe 0.5, you believe 0.5. But the truth, if we could just aggregate our information, is either at 1 or at 0. One thing we showed is that if you have signals that are substitutes, and it's a slightly different definition, again, of substitutes, basically this agreement process will imply that you're actually very close to the posterior condition on all your information. And that could happen in a conversation between Bayesians, or it could happen in the market. The theorem would apply. So substitutes are cool. That's a biased take.
Very close?
Yes, so after, let's say something like 1 over epsilon squared time steps, you might be within epsilon. You know, the information structure can be arbitrarily large, and yet after a sort of fixed time, you're within a fixed distance. And there's a related work of Scott Aronson in computer science about how fast you get to agreement, where he first proved you get to agreement quickly, and then we added, and you get to accuracy quickly if you have substitutes. I keep putting off data. We got to talk about data. So data setup. It's okay. You know, I'm going to stay close to what we've done so far. It's not going to be, you know, massively different, but hopefully, you know, this leads into some good discussions going into tomorrow, where we get to talk about data marketplaces kind of more broadly. This I'm going to focus on this perspective on data here and information's value. So data are pairs x, y in the set curly x, calligraphic x cross calligraphic y. a hypothesis is a function. I feel like this is an old word now and we only say model. From X to, well, let's say a report space, calligraphic R. So we can think of labeling images. X is the features, Y are the labels. So X is, for example, the pixels of an image or some features that are computed from it. Y is the label of the image. You know, does it have a giraffe or does it not? A hypothesis takes the features and maps to a report space, which could be the label space, but it could be something different. We'll talk about a quick example or two. And a loss function is just going to be some L that takes in one of these reports, and it takes in a true label, and it outputs a real number, which is your loss or your error. You made this report. The true label ended up being this. This is your error. Of course, we've seen this format before. This is the same format as a utility function, as a scoring rule when this report space is the simplex. And yeah, we'll say more about it. But in particular, your loss of a hypothesis H on a data point XY. So I'm predicting H, I'm kind of H, my hypothesis is my predictor, and its loss is L of H of X comma Y. So let's make sure that all tracks. Examples. The simplest machine learning type example is 0-1 loss. Okay. Here, the report space is equal to the label space, and the loss on RY, I can just define the loss on RY is going to be an indicator for being incorrect. You said not giraffe. It was a giraffe. Well, okay. You said lion. It was a giraffe. Your loss is 1. You said giraffe. It's a giraffe. Your loss is 0. You said, you know, something else. Yeah, it's on. A variant of this is abstain loss. And here the report space is just slightly different. It's going to be Y union. I'm going to reuse this bottom symbol to denote a null report. It's going to be abstaining from predicting. It's going to say, I don't know. The loss of a report, well, if you say the null report, I'm going to give you loss 1/2, no matter what. If you say another report, otherwise, I'll give you the 0-1 loss. Okay. Let's talk about these. I can give another example later if we want. I think, yeah, I want to recall to your mind the idea of property elicitation or elicitation of properties that was mentioned on Tuesday. Excuse me. The idea was we have some scoring rule for something like the mean of a distribution, the median of a distribution, ideally the variance of a distribution. Turns out we couldn't directly elicit that. The property it elicits is, does it actually, do you actually maximize expected score by reporting the mean, by reporting the mode, the variance, or whatever it may be. And as you recall, a property induces this partition of the probability simplex into the different reports. So example, 0-1 loss. If we take our favorite simplex on 3 outcomes, we can track, okay, let's say this is giraffe, lion, and what else, cheetah. We can track all the distributions that maximize expected utility, or in this case, minimize expected loss by reporting giraffe. It's going to be distributions in this top region. Why is that? Well, it's distributions where the mode, the most likely outcome, is giraffe. And indeed, you minimize this expected loss by reporting the mode. So your hypothesis class should map the features to the most likely label, the mode, if you're being evaluated with 0, 1 loss. Okay, and you have this region as well, and you have this region as well. Abstain loss is a little different. You can think for a second of what it's going to look like. So I want to report giraffe until what point of uncertainty? My belief that the probability it's a giraffe drops below 1/2. In here are distributions where giraffe's still the mode, it's most likely, but it's less than 1/2. My sort of posterior condition on x less than 1/2. I'm not going to make that formal. This is what that one looks like. There's this region in the middle, and both of these are Voronoi diagrams or power diagrams. Both of these are properties that are elicited by loss functions, in fact, these two loss functions, and so on. One more comment, by the way. If you have a decision problem, like take my umbrella or don't, or take the bus, walk, drive, those are different actions. You have a utility function. It's the same object as a scoring rule. It's going to induce one of these diagrams, where a region is where the optimal action is, right? So this region I should take my umbrella, this region I should not, or so on. So all of these things are the same. The loss function, the utility function, decision problem, scoring rule. They all have this structure.
So what is the difference between data and information?
Right, so in my talk, information, what I want to say is, I will either think of information as Bayesian signals, and I will do Bayesian updates. That was everything up until about now. Or I will think of information as data, and I will use a learning algorithm to make updates on that information. Thank you very much for this question. It's the right time. Here information are Bayesian signals, and the market prediction updates with a Bayesian update posterior. Here, information to my algorithm are these demand bundles, and I update on that information using a machine learning online no-regret algorithm. And that's the analogy that I want to draw today that's the key analogy that I want to draw, and I want to make that kind of formal in the way that it's formal here. It's a very tight analogy here. And we're going to get to this updating. We're going to talk a bit about that. I mean, we're not a lot left in the day. Yeah. Yes. So let's do that, and then we'll pretty much conclude. Something that, if it was a 4-hour lecture, we would cover now. We could talk more about relationships between loss functions. So Jason mentioned indirect elicitation. I maybe can't elicit something, but I can elicit something else and use it to compute it. Also, often in machine learning, I can elicit 0, 1 loss, this loss function, but I don't want to, because I can't run an optimization algorithm over this loss. It's discrete, it's not convex. So I do something like hinge loss. It's this convex loss function. I minimize it, and I hope that when I minimize that, my 0, 1 loss is also good. And the theory of elicitation can talk about whether that hope is a good idea or not, because the hinge loss, you can say, has a relationship to the 0, 1 loss, such that minimizing it causes you to minimize 0, 1 loss. Since I'm saying all this out loud, I'll mention one more thing I would have liked to say. It's in the notes. You can't necessarily do that in small dimensions. So if there are n possible labels, you may need a convex loss in dimension Rn, or Rn minus 1, let's say, because a simplex has n minus 1 dimensions. But sometimes you can. It turns out one of the basic key results, for mode you can't, for 0, 1 loss, you need n minus 1 dimensions for this surrogate loss, like this hinge loss in high dimensions. You have to do n minus 1, no matter what you do. That's a theorem if you're trying to use a convex loss to elicit this. Okay, I'm going to finish saying it and move on. So stay confused.
It sounded super interesting, so I really want to know what you're saying.
Yes, okay, I'll restate it and then move on. There's a notion of indirectly elicit where I want to elicit this. First, I use a different loss function. I minimize that loss. I take whatever I report or prediction, and I plug it into, or I transform it and plug it into here. That's like an indirect elicitation style. A question is, what kinds of losses, you know, if I give you 0, 1, what's the space of possible losses that you could use as a surrogate in this way? In particular, if they're convex, one question you can ask about them is, what dimension do they need to live in to properly mimic this loss, which has this kind of diagram associated with it? If there are n labels, which is very large, like the number of possible objects in an image, the dimensionality of any convex surrogate, there's a theorem, has to be at least n, or n minus 1. And which is cool.
What dimensionality are you talking about?
Right, so a convex loss takes in a prediction in Rn, in Rd. So I have a surrogate loss L prime, and now the prediction space will be R to the D. And I will say this indirectly elicits this if there's some relationship between them that we won't get into.
And here the space was R.
Here the space was a discrete space with n. It was Y, sorry, yeah. So here the discrete space.
And here you have a space of size exponentially.
No, just linear. So claim for 0, 1 loss, D has to be greater than or equal to size of Y minus 1 for indirect elicitation to be possible, which I haven't defined. With a convex.
Why is it useful then?
Why is it useful to my talk? Or?
Because L prime will be smoother than L, I guess.
Oh, so this is it's useful because this is a discrete object, and that my machine learning algorithms can't compute its gradient, and they can't optimize over it. But here I can have a continuous.
Smooth optimization.
Yeah, it doesn't necessarily need to be smooth. Like the hinge loss is not smooth.
Okay.
I better move on quickly, but
Okay.
you can study this question. You can study the dimensionality that one can use.
So the dimensionality should be big.
Yes, so it's a problem. This is a negative result that is known. It's a problem, and we want to fix it. It turns out abstain loss is a nice fix to that. It's mentioned in the notes. Sorry to mention this and then go to somewhere else, but we got to do markets for data intro so that you're set up for tomorrow. Okay, we're not doing anything really technical here anymore. We're kind of reinterpreting what we've done so far in this kind of context. I would say it's not really going to be technical. So value of data, according to this very specific kind of philosophy, is going to be the following. I'll kind of skip to a conclusion. Let's say A is a data set. Okay, let me put it here. A is a data set.
X plus Y?
Yes. A subset of X cross Y. And let's fix a learning algorithm. You have some learning algorithm that you like. You have some class of models or neural networks. You have a gradient descent algorithm you like. We'll kind of fix it and just say it's fixed. This is stylized, but so HA is going to be the hypothesis you learn training on A. H sub A is the algorithm outputs H sub A. It's a hypothesis. If I gave you two data sets, A and B, you would have H sub AB. The analogy is to the posterior belief P sub A, P sub AB. And now the value of A we can define, I'll leave off my superscript, as, okay, we'll take the expectation over, okay, let me back up, or let me go from the inside out. I'm going to look at the loss that this hypothesis would have on a new data point that is drawn from, okay, I didn't write this, let's suppose that there's a ground truth distribution. The exact model won't matter because I'm not going to make claims, but let's suppose for concreteness, there's a ground truth distribution pi, and on pairs. Let's suppose, even for more concreteness, that A is sampled IID from pi, but in real life, A may come from somewhere else. The value of A is going to be how well you predict on a new sample. So it's going to be the expected loss when x, y are drawn from pi of a new sample of your hypothesis that you trained on the data set A. That's going to be my definition of value. And I'm going to make it negative because more loss is worse. And so now it's in the format of a utility where higher value is good. Okay, and now...
so HA may not be the best algorithm for L.
Yeah. So I'm kind of throwing out my Bayesian framework. I'm not being Bayesian optimal at all. This is what I have to work with. Okay. I have this learning algorithm to work with. And now in this setup, I can think about concepts that we've talked about today, such as marginal value of information, by saying that I have a data set. If I have a new data set, how much will it improve? This is called the risk in machine learning of my hypothesis. So training on that new data set, how much will it improve my hypothesis? That's the marginal value. And so I'm measuring value of information with this risk. Okay. And it's a good discussion to have about limitations. Okay, so what I'm going to say is I'm going to go to prediction markets again and use that format again in a different way with this context. And obviously, we're short on time, so we won't get super into it. First, let's fix a problem. The problem is I don't know this number. If you give me HA, this is some expectation over some ground truth distribution. So I'm going to assume I have a test data set. Well, it could even be a test data point, xy. Drawn independently from pi, that's secret and known to me and nobody else. And that way, if someone comes to me and says, here's a hypothesis, I have a way to measure how good it is, or at least I have a sample from how good it is. Maybe I have many samples, I have a big test data set. And so if you ask me, measure the value of this hypothesis, I'm just going to do it with the empirical loss by checking how well it performs on my sample. And we could call that like v hat of A is going to be like the sum, or you could average if there were multiple. But if there's just one, it's just going to be the loss of that on this particular data point. Ideally, you would average this over a test data set. Minus. Thank you. Good. Okay, so it's going to stay, yeah. Okay. We're getting, yeah. I have one more concept to say. The concept is longer than the span of time, but the words are not. Then you have all of lunch to absorb the concept. Procuring data. Here's a proposal or an idea that's pretty straightforward with this. I have a test data set. Okay, I have an initial model, H0, in rounds T. Agent T arrives, or some agent arrives, and updates or reports a new model, a new hypothesis. HT. Then I'm going to stop. How am I going to reward the agent at time T? Yeah, so I'll pay them, pay T, the difference in loss. So it's an improvement in loss, so I kind of have to switch around terms. HT minus T-1 of x, y minus loss HT of x, y. I flip the T and T-1 because loss is negative instead of positive. If your loss is smaller than it used to be before you got there, you get paid positive amount. Okay, and so that's it. This is my market for procuring data. And now all the concepts we talked about apply analogously as they did in prediction markets to this market for data. People are paid for the marginal value of their information. You can think about substitutes and complements. Do people want to rush to provide data, or do they want to wait? Because the marginal value of their data will be better later than it is now, like something will happen. That could all depend on the learning algorithm. It could depend on the data. Is this data all IID, or do some people have data from some sources, other people have data from other sources? It's not IID. So all of that can be complex and can really change this from the Bayesian case. Okay, but we can draw all these analogies, and we can think about value of data in this way. Excuse me. Okay,
It's enough for me to take just one value.
Let me clarify something. Here I've phrased it as the agent reports an entire new machine learning model, but actually they could just report a data set, AT, and then I can use my learning algorithm to make HT equal to H sub everything so far and AT as well. Excuse me. Actually, you can run this in the way that I initially said and let people provide their own machine learning models rather than using my learning algorithm on data. And so this is a proposal of Abernethy Frangillo that they call collaborative crowdsourced machine learning contests, where we all collaborate to provide machine learning models one after the other. And your reward is going to be how much you improved performance on the test set. And indeed, this is a similar idea to what machine learning competitions like Kaggle do, but those are not collaborative, they're competitive. Everybody separately submits models, and the best model on the test set wins. Whereas here, we're sort of collaborating, and we each make updates to the model, and your payout or your reward is your marginal improvement.
Why do you need to observe what the others
So hopefully you're doing, why do you need to observe what others report? Hopefully, analogously to here, you're doing updating. Hopefully, when you see someone report an update with a new model, they seem very confident. You're updating in some sense. Maybe you feed some data into it and you use that to train your model to be more like theirs, hopefully.
So people here will be publishing step-by-step data. And
Yes,
and we need to know if your marginal data that you give has some value given the data that I already have. To train, you can also take all the data together, because if
yes.
the data will be substantial.
Right. So
Let's put all this together.
good.
That's what you have here.
Actually, I do want to talk about this last. Yeah, you can.
A1,
So this is procuring data one set at a time. And similarly to the prediction market, you could just set this up by saying, I have a big pot of money to pay for data. I have an initial hypothesis. I have a learning algorithm that is fixed. Give me the data, you're going to get a reward, assuming it actually helps me, improves my. And then people may be motivated to go collect data from difficult to collect places and give it to me. Whereas if I just said, give me a pot of data and I'll sort of pay everyone equally, I may not get that valuable data.
For all these problems you mentioned, you said that nobody is modeling precisely the cost of getting data and having all this included in the model.
So in the Bayesian setting, I don't think I've seen very much at all of that.
Okay.
Here, I think, and Rachel might even have things, I mean, actually you might have a paper even in this kind of setting, but, or like a crowdsourcing setting. It's, I think Rachel and others have papers where agents have cost of effort. Do you want to say more about that now?
No, because I'm going to say more about it tomorrow.
Yeah.
So.
Okay, good.
Yeah.
So that'll, I know we didn't have a lot of time to sit with this. Okay, I promised to mention something that I want to mention now before I stop. It's related to this comment of, you can also think of this as, so it's collaborative. We all come with our data and we all get rewards. You could think of it as a fairness problem. How do we split the rewards from our data, right? Okay, well, if I say a fairness and collective problem, there's only ever one answer, which is the Shapley value. And there's this concept called data Shapley, which is applying a very similar setup, where here you're rewarded for your marginal benefit whenever you happen to arrive. Maybe that's unfair, like you happen to get there early, you got lots of reward, your data wasn't even that good, but early on there's room. The Shapley value, some of you have seen in cooperative game theory, says basically your contribution to a collective, your reward should be your average contribution over all orders in which people could arrive and make a contribution. So sometimes you arrive early and you make a big contribution maybe, or sometimes you arrive late and still make a big contribution. Your average over all the orders. You can do the same thing here where you just average over the orders of the data. That's the definition of data Shapley. It's considered a proposal sort of for a fair way to compensate people, reward people for data. So yeah, and you can imagine thinking about other things to do in the framework. So let me conclude. We've seen today a lot on Bayesian information and how it's structured and value of information, definition of substitutes, which is relevant to these markets for data. So one way to phrase prediction markets is, I'm using proper scoring rules to elicit truthful information. Turns out to not be that far from, I set prices, people buy what they want, and I use a learning algorithm to update. That's my data that updates. Turns out to not be all that far from, we have machine learning models and people provide data sets and we train on the data sets and we pay them for the data in some marginal way. And there's a lot more thinking I think that we can do here, but that's where I need to stop for today with one additional brilliant comment.
Sorry, this L, can we link this L here? Because here you put R is equal, it can be delta of Y. We can have here proper functions. Question is can proper function be introduced also here in this problem?
Like a proper scoring rule?
Yes, proper scoring.
Yes. So here's how you could think of, these should all be proper scoring rules. Yeah. They may not be strictly proper because they have these regions where it doesn't matter. Yes. And the reason I wanted to talk about the kind of surrogate, like you have this one, but you have one that's related to it, is that could be helpful here. Maybe I want to substitute this out for something that better incentivizes certain types of information.
And when you say let's move to the R to the power D, it's just you replace L by something in the space of probabilities, something like that would be
yes.
The transformation you are going to do?
Yeah, we can talk more offline. Thank you. All right, I'm glad to talk more, I really appreciate it. We're coming back in just 1 hour. I mean, if you come in a bit late, we're not gonna be mad. For recitation,
eat quickly,
so we can.
and so I'll come back in 1 hour.
Yeah. Thank you all.